All right, so we talk about side channel analysis. Now it is a good time to talk about basic hardware design, right? Because physical attacks target the physical implementation of a chip. In fact, the attacks specifically exploit the way the hardware is built. It is the nature of physical attacks that they target a system as whole with all its details. To understand the attacks, it is necessary to have a basic understanding of a system from the transistor to the application. That is the whole idea. This is why you have to know your processor, okay? And I will focus on this in a few minutes. So the vast majority of IC designs are synchronous designs. Properties of synchronous designs are as follows. There is a state stored in memory elements, like registers, RAMs, flip-flops. There are combinatorial circuit elements that can do computations. There's a clock signal that triggers to update the memory elements. Synchronous systems are essentially a finite state machine that is triggered by the clock signals. Okay, this is important. We have to know the design. So a typical design is like this. So I have again need to thank actually Stefan Mangard. I'm actually using a shortened version of his course slides titled Secure Implementation of Cryptographic Algorithms. So here we have a block diagram of a typical security integrated circuit, okay? So as you can see, there are interfaces here, memories here, like flash, RAM, ROM, etc. You have the core here, the CPU, peripherals here, but more importantly, as you can see, we have security components here. And you can see things like true random number generator. As we mentioned before, when we talk about MyFair Classic smart card, you need to sometimes need a random number generator because most of the time you need a nonce. Here you have a coprocessor for algorithms like RSA, ECC, public key algorithms, or symmetric key encryption algorithms like AES, DES. Filter, sensor, pseudo-random number generator, or coprocessor for hashing. So this is actually a typical block diagram of security IC. Let's focus on the development process of a hardware. Up to a certain level, the design of digital hardware is very similar to the design of a software. Like in software, abstraction is used to cope with the high complexities of today's systems. During hardware design and manufacturing, there are many levels of abstraction. The design process typically first starts by completely modeling the hardware in software. The high-level model is then continuously refined until there is a description of the design at register transfer level, RTL. At RTL level, digital hardware is described using so-called hardware description languages like HDLs. I mean Verilog VHDL, for example. At this level, hardware can essentially be viewed as a finite state machine that updates its state in each clock cycle. For each manufacturing technology, typically a library of logic gates is created. Each gate is able to perform basic operations such as NAND, NOR, etc. The synthesis tool maps the functionality described in HDL to the logical gates of the library, right? The output of the synthesis is a netlist. Essentially, it's simply a graph where each node corresponds to a gate. Okay? So let me explain what the netlist from Wikipedia. In electronic design, a netlist is a description of the connectivity of an electronic circuit. In its simplest form, a netlist consists of a list of the electronic components in a circuit and the list of nodes that they are connected to. Okay. Layout. In the next step, the gates are placed and connected. In this step, many physical aspects need to be taken into account, like close placements of gates that are connected, minimalization of routing overheads, coupling of wires, etc. The layout is a geometrical description of the design. It describes which material should be placed where. Okay. After the layout has been created, it is sent to the semiconductor fabrication plant. Current technologies for security ICs are, this actually with the nanotechnology goes to smaller and smaller. Wafer sizes 200 nanometers, 300 nanometers. You know, this green colored stuff you see on your board. In electronics, a wafer is a thin slice of semiconductor, such as crystalline silicon, used for the fabrication of integrated circuits and in photovoltaics to manufacture solar cells. The wafer serves as the substrate for microelectronic devices built in and upon the wafer. Okay. Solving, testing, and packaging. After the wafer has been produced, the following steps need to be conducted. Solving, cut the individual ICs out of the wafer. Testing, no manufacturing process is perfect, hence it is necessary to test each IC. As all the functionality needs to be tested, this essentially means that there is unlimited access to the chip in this mode. So it is a serious problem if an attacker can get a chip into test mode, right? So actually the problem is two ways, because sometimes you build these chips, I mean, not sometimes, almost all the time, built in China, right? And you test it, and it passes all tests. But can there be a backdoor so that it passes all tests, but maybe 1 month later, the chip will work in a different way? Okay, so this is a huge problem. And currently, people trying to discover this kind of backdoors if there are any. So it is an important research topic area, actually. Packaging, the IC is finally packaged and ready to be shipped to the customer. Also, again, at this point, years ago, I remember that there were some people in players of World of Warcraft started to lose their monies, in-game goals, by the way. It turned out that they bought a hard drive, they unpacked it, an external hard disk, and they connected it to their computer, but it turned out that at the factory level, somebody put a Trojan in those hard drives. So that Trojan actually captures the World of Warcraft account password, and this way, people lost gaming goals from this. So this stage actually is a security problem, as you can guess. Optimization goals. All the tools and manufacturing steps have been developed with the goal to optimize the following properties. Area. The area of a chip is directly proportional to its cost. Hence, every saving in terms of area maps directly to the money. So this is actually our point in the first place, right? So making it smaller makes it cheaper. But if you want to introduce security, you have to add more stuff, so it will become more expensive, right? This is why there are many IoT devices that are very cheap, but do not come with any security at all. Okay. Throughput. Whenever there is a chance to optimize the performance, this chance is used in a design. Power consumption. The power consumption is critical, especially in contactless applications. Okay. So data dependencies in software. This is an important topic. Obtaining different timing for different data in software essentially means that there must be different execution paths for different data, right? In other words, depending on the data, not always the same sequence of instructions are executed. Do not perform conditional branches that depend on secret information. So this is the thing that we can say when we are talking about side channel analysis, okay? So if there is a branch depending on the key, then you lose everything. So this is why we always try to convince people not to for instance, choose S boxes depending on the secret key and so on. Okay? So do not use while statements that use secret values in the loop condition. For example, string comparison. Do not perform conditional branches based on key bits, as I already mentioned. Do not perform conditional branches based on intermediate values of a cryptographic algorithm. So as you can see, branching is a problem. So you want to implement it in such a way that there is no branching, okay? Data dependencies in hardware. So the previous one is for software. So throughput is one of the main optimization goals when building hardware. Throughput optimization is not something static that only takes place during the hardware development. Typically, there are several mechanisms built into the hardware to optimize the throughput during the execution of the software. Not every instruction always takes the same amount of time to execute. So this is very important. So even if there are no data dependencies in the software, the hardware might add data dependencies. okay, because due to this timing, okay. So for instance, you might say that, okay, there's an XOR operation, and then there's a, I don't know, multiplication. So it is both of them are single instructions, but maybe multiplication takes longer, right? So this way you're actually introducing data dependency at the hardware level, but not at the software level. Architectural components that often lead to data-dependent behavior on embedded devices are functional units and cache. So this is also very important. So if something is in the cache, since you are going to read it from there, the reading time will be really small, right? But if it is not in the cache, you have to go to the RAM and take it from there. So it will take longer. So if something happens in a fast way, then you can guess that, okay, this data comes from the cache. So this gives information, timing information, and also data information to the attacker. So, you know, using the cache is sometimes problem. And always also some attacks uses this too. For instance, in some CPU designs, in order to get more speed, some CPUs actually, when there's an if statement, and if you have two cores, you know, they both of them execute regardless of which path you are going to take. Then when the data comes, one of them is followed. But you know, actually the CPU performs both of the branches. So this actually makes a data leak too. Okay. Okay, for this reason, you have to know your processor. You have to know how it performs operations, which instructions there are, and so on. So for secure implementation of cryptographic algorithms, it is necessary to know the timing behavior of the underlying hardware. So at the GPU level, I'm actually good at it because since I have to optimize everything, I try everything, and I know that which operation takes more time than the others. Okay. But for this kind of devices, so since there is no documentation most of the time, you have to discover it by yourself. Problem for programmers in practice, things such as the exact timing behavior under all possible circumstances are not so critical for normal applications. Hence, not always the hardware reference manual contains all necessary information. This is also valid for GPUs, actually. So in some architectural changes, we realized that some of our codes work faster and sometimes it's slower, regardless of the main changes. For instance, two GPU series, both of them have the same number of cores, same number of clock speeds and so on. But all of a sudden, you realize that your code works on a lot faster on one of them and not the other. Then you realize that some memory operations are somewhat faster in one of them. Okay, similar thing happens to embedded devices. So double check timing behavior when you rely on certain properties, especially when you are implementing cryptographic algorithms. Okay. So I briefly mentioned cache, so let's focus on it more. The basic idea of a cache is to buffer memory content inside the processor. So a cache is actually next to the CPU, but you know, memory is kind of far ahead, so it takes some time to communicate with the memory and bring some data from there. So caches are used for two reasons: performance. Accessing a data block in memory is significantly slower than a cache access. Power consumption. Accessing a data block in memory consumes more energy than a cache access. So caches can be implemented as data cache, instruction cache, unified data and instruction cache. And there are many cache sizes, you know, starting from 1 kilobyte up to several megabytes. So nowadays our CPUs comes with many megabytes of caches. Yeah, on PCs there are multiple, typically 3 levels of caching, like L1, L2, L3 cache. For example, this Intel CPU has 20 megabytes of cache. Okay. So at this point, as you can see, it is important because these are two good stuff that the cache provides us, because you know it consumes less power and provides faster speed. But as you can see, now I can perform timing attack here and I can perform power analysis here. So caches are problems, or you know, sometimes might be good for the attacker to exploit. Yes, power analysis attacks on implementation of symmetric cryptography. The basic idea of power analysis attacks is to determine the secret key of a device by observing its power consumption during the computation of a cryptographic algorithm. Power analysis attacks are very powerful. unless explicit countermeasures are implemented. Every implementation can be broken. Power analysis is cheap. For an unprotected implementation, all that is needed is a PC and a cheap digital oscilloscope. So you can buy one for very cheap. These are small devices. You plug it by USB, but they're not capable much. So if the implementation is protected, you need a better device, like high-end standalone scopes, but they are more than like 30,000 euros. So this way you can actually plot the power consumption, and by looking at the plot, you can capture intermediate values of a cryptographic algorithm, and this way capture the secret key. Some part of it is sometimes the whole secret key.